So now we can talk about some pressure vessels. And we're going to start off with cylindrical pressure vessels. And why is it useful to talk about these? Well, it turns out that if you have a cylinder or a sphere and you fill it with some pressurized fluid or gas, if the wall thickness of your pressure vessel is thin enough that you end up with a pretty much 2D stress state. You end up with that state of plane stress. And our requirement is that has some geometric requirements. We'll get into those. But it's nice to stay in 2D here to kind of think about some of these transformations. So I'm going to draw a picture here. This is my cylindrical pressure vessel. All right. And it's got some inner radius. So I'm going to kind of draw that down here. So I'm going to call that R. And it's got some thickness, T. So that's going to be the wall thickness. So I might end up having some kind of wall thickness that looks something like that. Okay, and this thing has caps on the end, and it's got some axis, and it's a cylinder, so it would probably be in cylindrical coordinates. So this would be Z, and it's a symmetric problem. That looks like an N. This is a Z, and we have some kind of axisymmetric problem. So inside our cylinder, we have some pressure, and that's exerting a force on the inside of our pressure vessel. It's also going to have some pressure here on the faces. I guess I should maybe give this guy a little bit of a 3D aspect to it. We have some pressure that's acting on this face as well, and we have some pressure acting on the bottom here. So that's all due to some internal pressure, and I'm going to say that's P. And what I want to do is I want to consider some block of stress right there. And when I do that, we're going to calculate the numbers. What we'll find, though, is that we're actually already in a state of principal stress. We're going to have stress components in the longitudinal direction. We're going to call those sigma L. And we're going to have stresses in the hoop direction, or circumferentially. Call those the hoop stresses. And we're going to use some equilibrium to figure out what those stresses are. Just to as a reminder, that's the thickness is T. The inner diameter. It's important to remember that we use the inner diameter when we're talking about these problems, although the inner diameter is typically quite a bit larger than the thickness, so it tends to be a small error if you end up using the average or the outside. But for our problems here, we're going to stick to the inner. And just as a reminder that for thin-walled cylinders, if we want to make this assumption that R over T, so the radius divided by the thickness, needs to be greater than about 10. Okay? Any thicker than that, and we start to, this idealization that we're making here kind of breaks down. And so the question, again, is what are these stresses? And it turns out that we can do a couple of cuts or slices, and we can figure out what those stresses are going to be. So first off, let's go for our hoop stresses. So the hoop stresses are going to be constant. They're going to be the same all the way around, circumferentially. So let's draw a picture that looks something like this. See if I can see how good my drawing skills are today. All right. So there's our tube. Okay, to help us to illustrate what that looks like, I've brought along another prop. It is a yogurt container here. And so essentially what we've done is we've sliced our yogurt container or our pressure vessel in half. All right. And so we have some kind of gas and it's exerting pressure uniformly everywhere. And what we really want to figure out is what the stress is in our plastic, yogurt container plastic here in the wall. And that's going to end up being, if we cut it in half, that's going to be horizontal on both the top and the bottom. And if we think about our gas or our liquid, we could kind of trap. We could trap half of a tank or yogurt container full of that gas or that fluid. And if we made that slice, we would see that we have some kind of internal pressure that's acting to push that fluid or gas against the tank. So if we make this slice, all of the stresses that we're going to see on that slice are going to be going in the same direction. We're going to have stresses from our fluid or our gas acting that way, and we're going to have stresses in the wall of our yogurt container, which are acting that way. Now, hopefully your yogurt isn't pressurized, but hopefully you get the idea of what that looks like. So let's add some arrows to our picture here. So here's this interface along our slice, and we have some pressure that's acting on that, and that's just our internal pressure P. And then in the walls of our cylinder, we're going to have some stress, which is the hoop stress. So that's going to be sigma H. Okay, now the geometry here, just to remind ourselves here, the wall thickness is T. The sort of inside dimension here is going to be 2 times the inner diameter, 2r, and we're going to have another T down here. So I'll put some hashes in there so we can tell those apart. Okay, the last thing we need is some length, and it doesn't matter necessarily what length you choose, so I'm just going to give it a name L for now. And what we can do there is we can figure out what the stress that we want, which is sigma H, from equilibrium. So let's look at equilibrium of this guy. You can see that we're going to have hoop stresses that are going to be in tension because our pressure is acting that way. And if we want to figure out what those stresses are, we just need to equate the two. So this force is going to be the pressure inside the tank times the area of this orange rectangle, which has, let's start again. So we have the pressure inside the tank times the area of the orange rectangle, which is 2r times L. All right, so that's the pressure. So this is internal pressure. Okay, now we want to know what's the internal stress. So we know that there's going to be some stress acting. It's going to be uniform, sigma H. And what's the area over which the stress is acting? So we have a T up top, and we have a T down bottom. So we have 2T, that's going to be in one direction, and we have L going in the other direction. So that's L. And that there is going to be the stress in pressure vessel. All right, so you can see right away that we get to do a few things here. We get to cancel L, which is why I said it didn't necessarily matter what we picked. All right, we also have a 2 in here that we can get rid of. And if we do all of that, what we're going to find is that sigma H is equal to PR over T. Okay, so I'm going to box that there. That is our hoop stress in a cylindrical pressure vessel. Okay, so that is one of our 2 components. Remember, we're going for these 2 components there. The next one is the longitudinal. So this is for the hoop. This over here is going to be for the longitudinal. And I'm going to go back to our yogurt container, but now we're going to talk about the bottom. All right, so you can see we have our end, we have a little bit of that wall there. Now there's going to be some funny business that happens here at the corners, at the ends of our wall, but if we get far enough away from that corner, we're going to end up having kind of uniform stress again. So that's going back to that idea of St. Venant's principle. And so we're going to make sure that we're staying somewhere away from the kind of complexity of those corners. So we're going to end up being far enough away that everything's relatively uniform again. And so I'm going to see if I can draw this picture now for you. It's going to look something like that. And there's the thickness of our tube, and we've come some way over here, and we have our cap like that. Okay, so the same idea is true again. We have our cap, we still have some liquid in there or some gas, and we have some gas that's pressing against that with some known pressure. So all of our stresses are again acting in the same direction. We have this circle here in orange, and that has some pressure that's acting on it. That's P. And inside of our material, of our pressure vessel, we have some stress that's acting against that. Okay, and so we're going to call that sigma L for longitudinal. All right, and we can do equilibrium of that again. So if we look at the pressure, now we need to figure out the area of that. So that'd be pi times r squared times P. So that would be the force that's acting from the pressure. And that needs to equal to this force that's coming from our pressure vessel. And so here's one of the tricks that you get to use if you're using a thin-walled pressure vessel. You can assume that the area is just 2 pi r, so that would be the circumference times t. And if t is small enough, that's a pretty good assumption or approximation. So that's our area, that's our stress, and if we do some canceling, we can figure out what our stress is here. So we get to get rid of a pi and an r. And that's going to tell us that our sigma L is equal to PR over 2T. And that is the longitudinal stress. Okay. So that's pretty cool. So let's go back to our stress picture here. As it turns out, we're in a state of principal stress. So we have our sigma H up here, which is equal to PR over T. And that guy ends up being sigma 1. So our first principal stress, that's the big one. Our longitudinal stress equals PR over 2T. And that ends up being sigma 2. So to go back to our 2D picture, if we were to draw that in 2D, our more circle diagram here would look something like that. So this would be sigma 1 here, this would be sigma 2 here. Okay. One of the assumptions we've made in here is that sigma 3, which would be the out of plane direction, is going to be equal to 0. And this is our thin wall assumption. In reality, the stress has to go from the pressure on the inside of the tank to 0 on the outside of the tank, but that happens over a very short distance. And when the wall is thin enough, this tends to be a pretty good assumption.